Hi, welcome back to Biological Foundations. This is part two. We're going to start talking about parts of the brain, brain damage, and what that implication is. But let's go ahead and start with everything with a review question. So here's the review question. The fight or flight response is controlled by which system? The fight or flight response is controlled by the sympathetic nervous system. The sympathetic nervous system, which is part of the autonomic system. The other part of the autonomic system is the parasympathetic nervous system. So after the fight or flight response happens, then the parasympathetic calms you down and gets you back to normal. That's the parasympathetic nervous system. So today what we're going to discuss is why all this stuff about neurons and having to learn all the chemistry, blah, 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 why is that such a big deal? Well, the answer is because we have a fascinating system. We have a fascinating nervous system that can do and think and behave. But just to give you an idea of what it means for us to understand what's going on in our nervous system, the importance of it, we're going to move ahead and we're going to watch a video. Now, we're not going to watch about remote-controlled rats, though that is something that can happen. But we're going to talk about brain-controlled arms. So what I want you to do is watch this video, and then we'll talk about what it means. So in that video, you saw that the woman who lost her arm was able to get this new prosthetic arm that they were talking about. But what's important in this is the difference between the afferent and the efferent nervous system. Now, there's been a long time since we've been able to move arms and go out and tell arms to do stuff. We've been able to do that for a long time. And you'll even notice that this is a few years old. But what's important about this particular case is that this is a case where we not only have efferent, but we also have afferent information. Efferent means going out, right? So when you tell your arms to go out and to grab or whatever else, it's efferent. It's coming from the brain going out. Efferent, out. Afferent means coming back in. So afferent means that you receive the information. So I can feel this pen touch my fingers, right? That's afferent in reception. So what's going on in this particular video that was so important is that now she can actually receive information in a prosthetic arm. Not only she can go out and tell it to do what it's supposed to do, but she can feel. Remember, she closed her eyes, she could feel things. This is what we're working on and what we're starting to be able to do with our understanding of what's going on in the nervous system. It's fascinating, and you'll know that that's actually several years old. And so we're beyond that now and being able to do all sorts of important and fascinating things with between prosthetics and other things. Now, where does this come from? Well, it comes from us understanding how the brain works, how neurons work, and how we can use those pieces of information to help not only people with prosthetics, but also normal people in terms of parts of the brain, etc. Now let's go ahead and get rid of just a few things that just drive me crazy, right? So myths that people are propagating about the brain. If you ever hear somebody say that you only use 10% of your brain, you should tell them politely that that is incorrect. Why would you just use 10% of your brain? That doesn't make sense. Like trying to say, oh, I only use 10% of my heart. If that's going on for you, I'm sorry. You've got some big problems. You use your whole brain, right? Now, how active it is at any given time, that can change, right? Just in the same way that your heart can beat really, 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 really fast, or it can beat slow, depending on the need of what's going on. That 10%, that's dumb. Anyway. The other thing that really drives me nuts is this idea of left brain and right brain. And we're going to talk about where that comes from. But if you say, oh, I'm a left brain person, or I'm a right brain person, and so I can't learn that, boy, that drives me crazy. Oh, boy, it's not true. It's not like you got like this big, beefy bicep of a left brain, and it's just totally ripped, and this other one's like shriveled. That's not how it goes. You're using both sides of your brain. Of course you're using both sides of your brain. We'll talk about where that comes from, but you use both sides of your brain and you use 100% of it. So don't let people tell you otherwise. Okay. This is the part of the brain. And so I'm not going to go through all the different parts of the brain and each of their different functions, because there's so many different functions. We're going to go through some of the basic stuff that we need to know about. So the first thing that you should see is this on the left. That is a diagram of what it would be like if you sliced my brain in half, right? Sliced it this way, and you're looking at it sideways. Okay? That's the way you should think about it. Sliced and looking sideways, right in the middle. What I want to make sure that we are clear about is the difference between the cerebrum as well as the midbrain and the hindbrain, right? So what is normally called the forebrain is really the cerebrum. So the wrinkly stuff on top, that is the cerebrum, okay? So you see all this wrinkly stuff? That's the cerebrum. Then we've got the midbrain going on here in the middle, and then we got the hindbrain. So the way you should think about this is the difference between you and a lizard is that you have a lot of the same hindbrain and even midbrain stuff going on if you're a lizard or a human. And these are things that keep you basically alive. Make sure your heart's beating correctly, make sure you have some sort of balance, that kind of stuff, okay? Your midbrain often is involved with things like memory, but also emotions and some other things like that. The real difference between humans and other species is going on in the cerebrum, in that forebrain part. So if this is, so let's say that this is, I know it's kind of hard for you to see if it's going in and out, but if this is the spinal cord, my arm is the spinal cord, and then this is the midbrain, the stuff on top, the wrinkly stuff on top, that is the cerebrum. Your brain and a pig's brain looks almost exactly the same. You just happen to have more wrinkly stuff, specifically right here in front. So when we talk about the cerebrum, we're talking about all the wrinkly stuff. The outside of the cerebrum is called the cortex. So the outside layer of the wrinkly stuff, that is called the cortex. The cerebrum, you see on the right, the cerebrum has different lobes. So when you talk about hemispheres of the brain and lobes, you're talking about the wrinkly stuff. You are talking about the cerebrum. So a frontal lobe, okay, the parietal lobe, occipital lobe, temporal lobe. You have lobes on both sides because you have two halves of your brain. So left brain and right brain, right? There is something down the middle called the corpus callosum, and that separates the two. Well, it actually combines the two. They're separated, and the corpus callosum is what lets them communicate with each other. Most of the information that we're going to talk about today has to do with the cerebrum and the different lobes of the cerebrum, the wrinkly stuff, the stuff on top. And it turns out that that wrinkly stuff seems to be what actually gives humans better capabilities to process different kinds of information. And how do we know that? Well, one of the ways we know that is through, let me get rid of the circles, brain damage and experiences that people have with brain damage. Let's talk about this guy. This is Phineas Gage. Phineas Gage worked on the railroad in the 1800s. Well, that pole that you see in his hand, he was using it one day, and by all accounts, Phineas Gage was a gregarious, he was a good worker, he was doing good stuff when he, at first, okay? Then, one day, they were trying to blast some, they were trying to break up some rocks with like gunpowder, right? TNT, that kind of stuff. And so what they would do is they'd take that metal rod and they pound it into the rock. They pound the gunpowder into the rock. Well, something happened. He was pounding this metal rod into the rock, and it sparked, and the gunpowder exploded and shot that rod through his brain. So this is actually Phineas Gage's skull. And what you can see is that Phineas Gage's skull is that the rod went up through his brain and out that hole. Okay? It went up through his brain and out that hole. Now you can see that his eye, his left eye, is closed right there. That's because it went through his eye and out that side of his brain. So there's actually a hole in his brain up here at the top. So pounding shot through, went through his brain. He gets knocked back, and then he gets up. And people are like, Phineas, you okay? Something just shot through your brain. He's like, yeah, I think I'm all right. Maybe I should go to the doctor. Like, yeah, let's take you to the doctor. They take him to the doctor. The doctor's like, this is interesting. It seems that you've had something go through your brain. He says, yeah, that's kind of weird, huh? So the doctor sticks his finger, I guess it's his left side, he sticks his finger up the hole in his left cheek and down in from the hole down here, and the doctor touches his own fingers inside of Phineas Gage's brain, and Phineas is conscious the whole time and talking to him. Why is this a big deal? Well, this is a big deal because the actual part of the brain that was destroyed in this case, was the frontal lobe. Remember, the lobe has to do with the cerebrum, the wrinkly stuff, the frontal lobe. It turns out that Phineas Gage's personality changed after that. He became a little more erratic, etc., after this happening. And by the way, he did, for the rest of his life, he walked around with the metal rod that went through his brain as kind of a walking stick. And the metal rod, as well as Phineas Gage's skull, is on display at Harvard University. You can go and look at it if you want to. But what really was important here is that we realized that the frontal part of the brain, it's not, you don't need every part of your brain in order to survive. Now, I'm not saying you should go and blow holes through your brain. That's not what I'm saying. What I'm saying is that in this particular case, that was not important for his heartbeat, for example, or his respiration. It seems that this frontal lobe was really what's helping him function with executive functioning, like decision making, and control over impulses that he had. Because later on, those things changed in his personality. This led us to say that, hey, maybe there is localization in the brain where most of what's going on in a specific function is happening in certain parts of the brain. For this reason, we know that there's several things. So, for example, occipital lobe has to do with vision, right? We know that there's certain things about the parietal lobe that has to do with sensation. We'll talk about those. And that the temporal lobe and the frontal lobe are two different things. So, let's talk about brain damage and the Broca's area and the Wernicke's area. On your left, this is the left side, right? On your left temporal lobe, you have two areas, a Broca's area and a Wernicke's area. The temporal lobe, we often think about as being verbal, right? And a lot of it has to do with these two areas. Now, aphasia means a lack of ability or loss of something. When somebody has brain damage, like a stroke in a specific part of the brain, they'll have different effects. So what we're going to do is we're going to watch a couple of videos about people with Broca's aphasia and Wernicke's aphasia. Broca's aphasia means they've had damage to the Broca's area of their left temporal lobe of their brain. And that's different than the Wernicke's area. Wernicke's aphasia is when you've had damage to the Wernicke's area of the left temporal lobe of your brain. And what you'll see is that they have different effects on language specifically. So let's watch Broca's aphasia. So when you saw that video, you saw that the man who had Broca's aphasia had trouble producing the language. You can often think about Broca as the same as boca, like the Spanish word boca or the Portuguese word boca, which means mouth, right? So he had trouble producing, getting the words out. It's like he understood what he wanted to say, but he couldn't find the words. He couldn't produce the speech. People who have damage in the Broca's area often have problems producing speech. That's different, though, than people who've had damage in the Wernicke's area. Let's watch that video. So the gentleman you just saw had damage to has a Wernicke's aphasia, has damage to the Wernicke's area of his brain. Now, in this case, he was able to produce speech, but the meaning behind it was wrong. He felt like he understood what he was saying, but other people were not understanding it. He was able to produce words. The meaning behind them didn't have the same effect. In Broca's area, that has to do with producing speech. In Wernicke's area, that has to do with producing meaning in your language. Now, this seems to be different. My understanding is that this still happens with things like sign language, for example, right? It's not just literally your mouth speaking. It has to do with the understanding of language. And now it does seem that these are particularly important on the left hemisphere of your brain, not on the right hemisphere of your brain. There's different things going on in the right hemisphere of your brain. And for that reason, people have talked about the left hemisphere as being verbal. Now, in reality, we know that both hemispheres actually contribute to this. There just happens to be some people who specifically have that localized. And by and large, you can assume that it's more localized in the left hemisphere of your brain. That's true. This is going to bring us to a separate issue later on, but different brain damage in different parts of your brain have come up with different effects. And so we can know more or less what's happening in different sections of the cerebrum and what they control. Let's go ahead and watch this video about prosopagnosia. So in that video, you watched a woman who has prosopagnosia. Sometimes we call that face blindness. Damage to her brain has led her to not be able to recognize faces. Now, she remembers things, but she just can't recognize faces, like not even her own mother's face. What's going on here is that there seems to be a part of your brain, specifically in humans, that is really focused on understanding and remembering faces more than other things, like the color of somebody's shirt, or maybe even a hairstyle or something like that. Let's not worry about constructional apraxia right now, but face blindness, prosopagnosia, is brain damage leads you to not be able to recognize people's faces. Synesthesia is when the experience of senses seems to be mixed. That is, that people could hear tastes or taste shapes, right? So the idea that taste is mixed with a visual concept of a shape. Something is being mixed in the brain to make those persons perceive those things together. The last example I want to show you is the split brain patient. Now, a split brain patient is one who's had their corpus callosum severed. So let's go ahead and watch this video. Now, in this video, you saw that the corpus callosum was severed because of severe epileptic seizures. Now, nowadays, we really don't do the severing the corpus callosum like this for severe epilepsy, but it does seem to have made an effect on the epilepsy. The seizures did seem to be more under control when they were severed. Now, the difference, though, is that now the left hemisphere of the brain and the right hemisphere of the brain do not talk to each other the same way. They are not communicating through the corpus callosum. So that means that they are processing information separately, even though they're as if they were almost two different brains. Whoops, sorry. So this means that when people see something, it goes to a different part of the brain. Now, this is what you need to understand with this. Your brain and the functioning of the brain goes across your body. So the right hemisphere of your brain controls the left side of your body. The left hemisphere of your brain controls the right side of your body. So what that means is information that goes through your right eye goes to your left brain. Information that goes through your left eye goes to the right hemisphere of your brain. Now, normally, you're seeing things with both of your eyeballs, and so the information is going to both sides of your brain. So in this particular case, when people have their corpus callosum severed, you have them focus on a dot right in the middle, right? Or you actually put a shield right between them so that the information only goes to one hemisphere and not the other. So if you have somebody focus on the dot, and so that only information is going to go to the left hemisphere of the brain or the right hemisphere of the brain, then they can look at two separate things with the two different eyes. So for example, here on the left, I have a star. Here on the right, I have a box. Okay? Let's see if that box is there. Now, let's assume that the split brain patient can only see the star with their left eyeball, and they can only see the box with the right eyeball. What happens is the star goes to the right hemisphere of the brain. The box, because it goes in the right eye, goes to the left hemisphere of the brain. Now remember, that Wernicke's area and the Broca's area is on the left hemisphere of the brain. And so when people have their language control on the left hemisphere of the brain, that means if you ask them, hey, what did you see? Then the part of your brain that can speak will say, I saw a box. Then you'll say, all right, reach out with your, now remember, this is, okay, the star went in the left side of your eye, your left eye, the right side of your brain, but my left hand is the one that controls, is being controlled by the right hemisphere of my brain. So you said, okay, what did you see? Oh, I saw a box. All right, now with your left hand, pick up your pen and draw what you saw. And when he does that, he would draw a box. And you say, well, what did you just draw? Drew a box. Why did you draw a box? I don't know. What did you see? Saw a star. How come you drew a box? I don't know. The information in the two hemispheres of the brain don't communicate with each other. Now, to be fair, this problem of split brain patient is extremely rare and happens only because we've had to do those surgeries. When a child, a young child, has to have part of their brain removed because of something like severe seizures, because of the plasticity of the brain, plasticity means flexibility, right? A child can actually gain control over different parts of their body even though they don't have that part of the brain. Now, if that would happen to you as an adult, you'd die is what would happen, right? But the child might have a slight detriment in being able, they might be a little bit weaker on one side of their body, but they're able to get language and other functionality because their brain learns to adapt, learns to make other connections with the parts of the brain they have and create a functioning human that can control different parts of their body. Because children are developing those synapses, developing those connections and all those things so that they can actually function without two full hemispheres of the brain. All right, review question. Which of the following connects the two hemispheres of the cerebrum? Corpus callosum. Corpus callosum does that. Corpus callosum. Last thing I want to mention is the somatosensory cortex. So on your parietal lobe, you seem to have, remember, cortex means the outside of the cerebrum, right? So there seems to be part of your parietal lobe that is particularly involved with sensing, right? Somatosensory, body sensation, with sensing different parts of your body. And so we can actually stimulate those different parts and you would have sensations in those different parts. You'll notice that your tongue and your mouth and your hands have a whole lot more space on that somatosensory cortex. Well, it turns out that those are particularly important for us, that we need to have, understanding of feel in our fingers, in our tongue, etc., more so than your elbow, for example, where you don't need to know how things feel. The thing that you see on the right is called a homunculus. It's a proportional representation of what your body would look like if proportionally the somatosensory cortex was proportionate to the actual parts of your body. You'd have a huge mouth and a tongue, you'd have huge hands, for example, because those are the parts that really need a lot of fine sensations in the human experience. Thanks, everyone.